Now that we understand weirs and weir equations, we're going to apply those ideas specifically to drainage flow monitoring. It is getting good now. Remember, the ultimate learning objective for all of this is to be able to make informed recommendations on how to monitor drainage water. You're familiar with what a control structure is and the stop logs that are inside the structures. These rectangular stop logs essentially act as a broad-crusted weir behind which water depth can be continuously recorded. The recorded water depths can then be used to calculate the flow rate flowing over the stop log using the appropriate weir equation. You might be thinking, though, measuring the water depth behind a stop log in a control structure violates some of the criteria for valid use of a weir equation that we just talked about in the last lesson. For example, that the pressure transducer should be placed in front of the weir at least 3 times the maximum expected head on the weir. Well, that's not possible with this tile pipe and control structure setup. And so in our case, that pressure transducer is necessarily close to the weir. In general, those limitations on the use of weir equations are valid. But for subsurface drainage monitoring, our stop logs have been pre-calibrated to act as weirs by setting up a control structure in the lab and measuring how different water depths over those stop logs correspond with different flow rates in that given setup. This allows us to develop a physical relationship that exists between the water height over the stop log and the flow rate moving through that drain pipe. This type of empirical testing in the lab allows development of graphs like this, where the x-axis is water depth above the crest and the y-axis is the flow rate. From the graph, you get an equation that you can use for your field data. This is valid to use for this application, even though we violate some of those conditions we talked about previously. Weir equations were developed for agri-drain control structures and their stop logs several years ago. For rectangular or flat stop logs, the equations depend on the size of the drain pipe coming into the control structure. For control structures that have a 6-inch diameter pipe coming in, you use one of these 2 equations, depending on how high the water is above the stop log. For larger control structures, you use one of the bottom 2 equations. For the majority of our monitoring sites, though, we don't just use rectangular flat stop logs that are the standard for normal control structures. We order a V-notch weir stop log to get more precise flow measurements at lower flow rates. The reason for using V-notch weirs is that if you have a small depth of water flowing over a flat weir like I'm showing here, it can be very difficult for pressure transducers to actually detect very small changes in water heights, like when the water goes from here, now watch the blue, water goes from here to here. Those are pretty small changes in water depths. However, if you change the shape of the overflow area, and rather than having a wide area for the water to flow over, instead have a triangle, all of that water flowing gets squeezed into that triangle and the water height relatively increases more when you have more flow. For example, in the V-notch weir, as your flow rate increases, your water depth would go from here to here. So you can see the difference in how much that water height changes, which is just easier for pressure transducers to capture. The most common type of V-notch weir stop log we use is this one with a stainless steel front edge. This thin front edge allows water to cascade more cleanly over the top of the stop log, so this acts as more of a sharp-crested V-notch weir. And the equation for this weir is shown here in both metric units on the left and US customary units on the right. I want to talk through the decision criteria for using the right weir equation at the right time in a control structure. These criteria are based on the water height above the stop log, which of course can vary day to day. Starting with the first scenario, the easiest one. The water depth you see illustrated is below the top of the stop logs. Clearly there is no flow, or put differently, the flow rate is 0. There's nothing going over that stop log weir. Even though this is obvious, mathematically you can also prove this by putting 0 in for H in this V-notch weir equation, a water height of 0 raised to the 2.28 power times 1.44 equals 0 gallons per minute. In the second scenario, the water level in the control structure is deep enough to be flowing over the weir. So similarly, you would use the V-notch weir equation. Remember though, H in the equation is not the total depth of water from the bottom of the control structure. H is only the depth of water flowing through that V. This H is illustrated with the little orange arrow. Here are the third and fourth scenarios where you see a depth of water that is completely filling the V plus water above that. This is where you would use a compound Weir equation, meaning you have to add together the V-notch equation and either the first condition, which is illustrated here, or the second condition, which is for deeper depths and is illustrated here. Here we also need to know the size of the control structure because you see those additional equations vary by structure size, and the width of the structure matters in these equations. The V-notch Weir equation is the same regardless of structure size for structures from 6 and up to 10 inches because the actual stainless steel V is the same geometry regardless of how big that plate is or how big the structure is. Starting with the V-notch part of this compound Weir equation, keep in mind that these two water depth conditions, the depth, or the H, that goes into the V equation is the depth of the entire V, because that V is flowing full in both of those scenarios 3 and 4. So the H, or the V part of the compound Weir equation, is 16.5 centimeters, or 6.5 inches. But we're not done yet in those scenarios because we need to know when to use either one of these other two equations to add on top of the V equation. The decision point here is based on the width of the structure and the height of water on top of the V. Assuming, for example, we have a control structure that fits to a 6-inch pipe, I know the width of that structure is 6.31 inches. So I know my decision point for which of these two equations to use is 6.31 inches times 0.44 equals 2.78 inches. When the water depth above the full V is less than 2.78 inches, I use the top equation. And when it's more than 2.78 inches above the top of the V, I use the bottom equation. The same type of decision point calculation using H and W applies for those larger control structures with the bottom set of equations. The last scenario is a completely submerged control structure, which can happen when the field is flooded. In these conditions, you often also have a submerged outlet downstream for the entire drainage system. Here, a Weir equation is not valid because there is no air pocket behind the nape when the weir is entirely submerged on the upstream and downstream sides. It's not uncommon to remove these flooded periods from a data set because there may not actually be water leaving the field due to the submerged outlet. To take a sidestep here at the end of this lesson, I wanted to show you an additional tile drainage weir application if and only if you have access to the outlet of the tile system you want to monitor. These small Thelmar brand weirs can be placed in a tile outlet pipe. They are pre-calibrated weirs that use a stage-discharge relationship just like every other weir. If you're interested in this type of setup, I highly recommend watching a transforming drainage video by the very famous Dr. Kevin King, where he describes how these work. I also want to take this opportunity to mention this transforming drainage video series because maybe you hate weirs and you're over weirs and you want to find some other way to monitor drainage discharge. Tipping buckets, pumping through a flow meter, velocity meters, there are other options depending on your application, budget, and personnel. These videos do a great job of presenting the pros and cons of each type of drainage monitoring system. Thanks for joining. I'll see you next time.